Recording in progress.
Yeah, comes on everyone. So last thing we did was this problem, which was a pretty good one. Hope everyone has gone through the notes once. So if you see last class, right, we primarily focused on, when the tension was constant, but what happens if the tension starts varying? That is one. Second thing, when we have force, there is also energy. So if you're going to pull this rod, if you're going to elongate them and compress them, they kind of behave like springs. So we have something called elastic potential energy. Now, consider we have a rod. Fixed at one end. It's pulled by a force F. And it elongates by E in equilibrium. So let's say we have a rod here, Young's modulus Y, area A, length L, and someone started applying a force F. Now what will happen when you start pulling it, the rod will suddenly not reach the optimal position. Others, do keep your cams on. So there is an intermediate position here. This will be X. This is an intermediate position. So the force is F, but be careful here, the tension won't be F. So there will be a tension here. What is the tension now? If you remember the formula from the Young's modulus, Y is equal to tension length by A elongation. So tension will be YAX by L. It's kind of like a spring, right? The more you pull the rod, the more the elongation. So and more the resistance from the rod. So it is applying more and more force, but F is still greater than T. Eventually, the rod will reach a position E. So this is your final equilibrium. This is your equilibrium state. So in equilibrium state, the external force F, your tension T becomes equal to F. This becomes YAE by L. So basically, as you're pulling the rod, the tension keeps changing. The external force is constant, but the rod which is resisting you, that is changing continuously. So tension varies with elongation. So if I ask you work done by tension, you cannot directly say tension into area, you have to integrate. This will be minus because tension is backward and the elongation is forward. This would be minus YAX dx by L0 to E. This would be minus YAE square by 12. This is work done by tension. But we know work done by internal conservative forces is negative of potential energy. Therefore, we get potential energy is YAE square by 12. Let's write it in more detail in the next page. But have a look at the derivation here. Are you getting this point? If I apply force F, why the tension is not F? Think of like this. If you have a spring where we know force is equal to minus kx, if I apply 100 newtons, but the elongation is still 0, does the spring care? The spring will simply say, I will apply the force as much I am elongated, right? I don't care how much is the external guy. But since the 100 is greater than the internal force, the spring will continue to stretch. So this will keep happening, right? And the tension will keep increasing. Have a look at this. Last class we have done with the force part. We are doing today energy and variable tension problems. All clear with this? You can put on the result. Don't worry about writing the notes. You'll get the PDF. So focus on listening, understanding, absorbing the concepts. And we'll be doing problems. So focus more on problem solving. Let's see. So we got the delta U, the change in elastic potential energy. Anyone confused with anything? You can always unmute and ask. YAE square by 12. I don't like this form. There is a better way of writing this. We can write this thing as half. Do remember, we know the tension is equal to force is equal to YAE by L. So this can be written as half FE. So that's one way of writing, right? You can do even better. Half F divided by area, E divided by length. So multiply area into length. Force by area becomes stress. E by L becomes strain. A into L becomes volume. So there are multiple ways of writing this. So this is your elastic potential energy. But more than this, I would like this one. I can write strain, and we also know stress is equal to stress by strain is Y. So I'll replace strain with stress. So this will become half stress square by Young's modulus into volume. Then we also define, this is a thing which I like, especially while doing integrations, right? You will notice this formula really helps us a lot. All right, so then we also define elastic potential energy. This is a small topic. We'll be wrapping it up, and I think next class we'll start off with SHM. Half stress square by Young's modulus. So these are the main things you can remember. This is one. This is one. This is also called as energy density. Mass per volume is called density. So this is energy density, especially useful for units and dimensions. Okay, you can note down that stuff. But remember, there is a catch with this. All these formulas are valid only when tension is constant. If tension varies, you can't use any of this. Clear, everyone? Any doubt so far? Anyone not clear with anything? You can just unmute and ask. If feeling shy, you can type in the chat box.
So didn't we find delta U and didn't we integrate it taking that X changes? So
Okay.
tension at every length is different, right?
Right.
So how then why
This
will
is an
this be?
equilibrium, right? What did you find exactly? What is this potential energy? When did you find potential energy?
Sure.
Did you find potential energy at every instant?
No. Okay.
You found potential energy in equilibrium, right? So you're taking tension in equilibrium.
Okay. Thank you.
So even in equilibrium, if you have a variable tension, which we will see later on, you won't be able to use this.
Okay. Thank you, sir.
Clear, everyone? You can note down the stuff in the red box. You'll be needing them while solving. Saumitra, clear with this? Pramiti, Kaushambi, Devika? Clear? Arush, Aditya? No. If you compare this with the spring block systems, you can see this thing. So we got y is equal to FL by AE. This looks like YF is equal to YA by L into E. You can see the resemblance. This thing kind of looks like F is equal to Kx, where K is the spring constant. So the spring constant is actually given by YA by L. Now, if you remember, in NLM, we did this thing. When you cut a spring, what changes? This is the reason if you have a spring, K and length L, and if you cut a spring, Y will remain constant. Young's modulus will not change for a material. Area of cross section, that this area will not change. So K into L remains constant whenever you cut a spring. So if you cut the spring into two pieces, the spring constant actually changes, becomes K1, L1, length is K2, L2. We get K into L is equal to K1, L1 plus K2, L2. Hope you remember this. We have done this in NLM. So that actually the relation comes from elasticity. And just to give an example, if you take a spring and if you, this is K and L, and if you cut into two pieces, let's say L by 3 and 2L by 3, the L by 3 ka spring constant will be 3K, length is L by 3 because the product must be same. And this guy will be 3K by 2 and this will be 2L by 3. So spring constant actually changes whenever you cut a spring. So for more details about this thing, you should definitely go back to NLM. We have done some really good problems on this. The same stuff, cutting off a spring, right? And then we also did springs in series, springs in parallel. What happens if you combine the springs? Quite a useful concept. We're going to use this in SHM next. I'm going to repeat there also once more, but you can revise this. And just keep a note there. You can check it out for reference. So there, so you can compare like this with spring. So if you even see the spring energy, spring potential energy is half kx square. And you will see the relation. This will be half y a e by l. So that is k and d square. Can you see this formula looks like this? So you get the same formula there. So it kind of looks like spring. Again, only problem, valid for constant tension. So even in a spring, we take the tension to be constant throughout the spring. If the tension is varying in the spring, we have a problem. So Ansh, what you're asking now, tension should not change with position. It can change with time. You're getting it? Let's say at the first second, the whole rod cut tension is 10 newtons. I'm okay with that. Next second, 20, I'm okay with that. What I don't want is, I don't want the left half have to 10 and the right half to have 20 newtons. So tension can change with time, but should not change with position. Everyone should have same tension at any point of time. Is this clear, everyone? Next one. Any doubts on this page? Anyone not clear with this? Tanish, Pushkal, Param, clear with this? Kush, Devansh? Perfect. Next thing, heat produced. This is one thing I keep telling you, nature, right? If you do something, the nature will always take away. It is like your silent partner. It's like our Indian government. It comes and takes the taxes. So this thing always takes away 50% of the thing, right? These taxes are always 50%. Remember in surface tension, we had this? When the capillary height was going up, we lost 50% of the energy, right? And later on, we will see in current electricity, whenever you put a battery to charge, you lose 50%. You take any case in science, like you lose minimum 50%, you lose. So the same thing happens here. Look at this thing. So when you take this rod and when you applied force F, and this was E and this was F. If you remember, the work done by the force is nothing but force into the displacement of point of application of force, remember? So work done by this external force is Fe, whereas the energy stored was half Fe. So the remaining half Fe became heat. So the reason for this, tell me one thing. If F and tension are not balanced, shouldn't the rod be accelerating? So technically speaking, this rod should be oscillating like a spring and block, isn't it? We don't see that happening. So all that energy was lost in the form of a heat. So heat produced is half Fe. You lose half of the energy. Clear with this? But there is an exception. They can ask this as a statement questions. Suppose if the F external force is slowly increased. Here we gave a constant force. Here F is constant. Instead of a constant force, if F external is slowly increased, that is F external will be always equal to tension, which will be always equal to YAX by L. Then work done by external will also be half Fe. Energy stored also will be half Fe. This was a statement question, more than one choice. If you apply a constant force, what is the heat produced? If you apply a force which is slowly increasing, what is the heat produced? Zero. Since you're applying it so slowly, there is no point of oscillation, so there'll be no heat produced. This is how they'll frame theoretical questions. At an advanced level, more than one choice, this will be one of the statement. Clear, everyone? So that is a little bit of a theory about this, the energy stored part. So till now, if you see, primarily we did two main things. One was finding elongations and one was energy. So let me just brief up the main formulas again. So if you have a constant tension, use these formulas. Elongation will be tension length by AY. And the energy stored, like I said, I prefer this half stress square by Young's modulus into volume. Why do I prefer this? Think about this. What is stress? Tension by area. So if I know tension, my job's done, right? Instead of using half of stress, strain, volume, you need to find stress separately, strain separately. Why you want to get into all that headache? So if you have a constant tension, this is how the formulas will look. If you have a variable tension, so if you have a rod like this is what we do for variable tension. At a distance x, take a very small slice dx. Because the tension is varying, I can't use the formula directly. So this is what I do. So I take this small dx rod. Since dx is so small, I can assume tension is constant. And let the elongation be dE in this small rod. Since dx is so small, that is the whole point of integration. You take such a small slice, you can think it is constant. It does vary, but a negligible change. We can assume tension is constant. So you have taken a small rod dx. dE is elongation in dx. Perfect. So look at the formula. So we are going to use the same formula. E ka place mein it will become dE. Tension is tension only as function of x. L ka place mein will get dx. So basically this E is the elongation in length L. Here E is the elongation in x by ay. Since you want full integration, integrate this. That's your formula there. So we get elongation is integral tension as function of x into dx by ay. Similarly, energy stored also will be integral of stress will be how much now? Tension by area whole square. So basically the same thing. Of stress square by Young's modulus, the volume will be A into dx because you're taking the volume for that small slice. There. These are the things which you use in case you have to use for variable integration. Check out that stuff. You have a variable tension, use this. Here, everyone. So if you see this formula, right, one thing you must have noticed, the main thing is somehow, if you can find tension, my job's done. That's what I keep telling you from the beginning. This entire chapter is 70 to 80% is finding tension. If you know how to find tension, your job's done. So let's say a question. So till last time we saw with constants, what happens if you have a variable? We got a rod. Smooth floor. Young's modulus, area, length L. Someone is applying a force F. Same thing. This is 2F. This is F. Smooth floor. Young's modulus, area, length L. Find the elongation and the energy stored. Try. Get the first one. I'll give 2-3 minutes. Meaning, I'll give you the steps. Step 1, find the tension in the rod as function of x. You can take x from left side or something. Step 2, put this in the formula and integrate. Try. Take 2-3 minutes for the first one, then I'll show you, then I'll give you more time for the B part. First, you try to figure out whatever it is. And in the end, I'll give you a shortcut. Do you guys find the tension? Let me help you with the tension part. See. Listen carefully in case you don't know how to find tension. So you're applying force F. So the system will be accelerating. A is equal to F by M. This is a common thing. Whenever you want to find tension, let's say at a distance x, you want to find tension. Cut it here. Simple story here. Wherever you want to find tension, you have to cut it. Because if you don't cut it, this will become a part of a system. Tension becomes internal force. You can't calculate it. Getting it? Only when you cut it, you get a slice there. Now, when you cut it, you'll always get two pieces, the left and the right. You can choose any one. So I will choose the right part. So when I choose the right part, now the forces will be F, tension, acceleration, and the mass is small. And mass has changed. The main thing is that the mass is different. What is the mass of this piece? Unitary method. The total mass by total length into this piece. This is the mass. Now, Newton's second law, F minus T is equal to mass into acceleration. This is F minus T, mass is m by Lx, acceleration is F by m. We get tension is equal to F into 1 minus x by l. This is how the tension varies as function of x. This would be an easy mains level question, finding tension itself. This is how you find tension everywhere. In case you forgot, should definitely go back to NLM. We did at least 3-4 varieties on this. So find the acceleration of the thing. Wherever you want to find tension, cut it there. Then you'll get two pieces. Whenever you cut, you get two pieces. Choose any one. You could have taken the left piece also. The mass would have been m by L 1 minus x. So you would have got the same answer. So once you got this, then we know elongation curve formula is integral tension as function of x into dx by ay. Substitute here. This guy would be f by ay is constant integral 1 minus x by L dx. X limits will go from 0 to L. This would be f by ay, that will be L minus L square by 2L. FL by 2ay. And for the energy stored, it is integral of stress square by Young's modulus into A dx. Stress is nothing but tension by area, so this is half F into 1 minus x by L by area ka square. Young's modulus A into dx. I can expand this. This will be f square by 2ay integral. If I expand that, I get 1 minus 2x by L plus x square by L square dx. If you see the integration is all x power n by integration only, this thing turns out to be f square by 2ay. That would be L minus x dx is x square by 2. That is also L plus L cube by 3L square f square L by 6ay. Check. That's how you do. And the main catch in the question is to find the tension. Once you find the tension, your job's done. Please have a look at the steps. And using these steps, can you replicate the second problem now? I have 2F and F. That is only difference. You have a rod with tension 2F, force 2F and F on either side. Now can you solve? I'll just write on the question pie if you want here. So we have a rod here. This is 2F and this is F. There. I'll keep the space there. You can see this problem as a reference and try to solve the second part. Try. I'll give 3 minutes. Find the tension, find elongation, find energy. The only difference, tension will change. All the formulas will look identical. Try. Everyone should try. Only when you solve it on your own, you will get a hands-on practice of putting limits and integrating. Finding tension is a basic NLM problem. It's okay if you don't know, but I taught you right now. At least try. The problem is most of you think like, if I start a problem, I should get till the end. All I'm saying is if there are 10 steps, at least figure out 2 to 3 steps. If you just keep staring and waiting for someone to come and help you out, you will become weak. You will never try to learn on your own. So put a little fight. Try. At least get a wrong answer. I'll give you another half minute for finding tension. If you got tension, then it is done. You just need to put it here, integrate, put it here, integrate. That's brute force actually. Let's see the tension part. 2F and F. Listen in case you didn't get it. First thing, find the acceleration. That is easy. 2F minus F by M. F by M. You want to find tension? Where? At a distance x from the right side. Fair enough. Cut it here. When you cut it here, you get 2 pieces. Previously, I took the right piece. I'll take the left piece if you want. I'll take the left piece. Now the forces are F and this is tension. What is the mass of this? So this length will be L minus X. So mass of this piece will be total mass by total length into L minus X. So we get tension minus F is equal to mass into acceleration, which is M by L into L minus X into F by M. So this thing turns out to be T minus F is equal to F into 1 minus X by L. Send F to T this side, you get F into 2 minus X by L. That's your tension. Once you got the tension, the elongation is integral tension T of x d of x by ay. Get this? Can you find tension and energy, elongation and energy? I'll give you a minute. No, it's just brute force integration. There's nothing to think now. So this guy would be f by ay integral 2 minus x by l dx. This is f by ay l minus that would be 2l minus l square by 2l. 3fl by 2ay. One a will cancel. This will be f square by 2ay. Integral that would be 4 minus 4x by l x square by l square dx. So this would be f square by 2ay. 4l. That will be x square by 2. When you substitute l, it will be l square by 2. So that will be 2l. This would be l by 3. That will be 2l plus l by 3. 2l plus l by 3, 7l by 3. 7f square l by 6ay. Anyone got the same answers? Yeah. Hansh, Om, Devansh. Okay. Check out the solution. Check out the working. Anything you're not convinced? Any step that you didn't get it? Calculation. Clear, everyone? So, like I said, the main thing is finding tension. Once you get tension, it is just a matter of putting there and getting integrating it. Any doubts on this? Amarpreet, clear with this? Rajesh, Prashant, clear with this? Navya, Archana, Aditya, clear? Sanchit, Tanish, perfect. Let's see something better. I told you a shortcut right now. Here we can do, if this comes in mains, right? You can do this only for elongation though. If you have a rod here, if you're applying force F1 and force F1, F2, we can take the average tension, T average is F1 plus F2 by 2. Suppose if it is pulling F1 here and if you're pushing here, F2, then the average tension would be F1 minus F2. Then you can write the elongation will be T average length by AY. Directly you can use this. Only problem, works only for tension, works only for elongation. Can't use for energy. And this I told you why it works. Mathematically, why it works. See, the reason why it works. Because tension is a linear function. Whenever the function is linear, suppose if this is a linear function, what do you mean by integration exactly? Tell me. When you say I'm integrating something, what do you mean by mathematically? You're actually finding area under the curve, isn't it? And when the function is linear, when you find area under the curve, what are you doing? What is the area of a trapezium? Of h1 plus h2 into this width, isn't it? So h1 plus h2 is the average midpoint, isn't it? So for linear functions, you can just take the average and finish it off. But suppose if this was some quadratic function, can you still say that average I will take? You get in the problem? So whenever you see the function is linear, for example, in this case, you can clearly see the tension is changing as a function of x linearly. And elongation, this is a power one function here, linear function. You can use this, works for elongation and not on energy. That is a disclaimer. You have to be careful. Don't use it for that. Doesn't work for energy. You have to integrate. So mostly at a mains of bits level, they'll ask you for elongation. Saves you a lot of time. Example, look at the question just we did. So if you're pulling with 2f and you're pulling with f, T average is 2f plus f by 2, 3f by 2. Elongation will be 3fl by 2ay. Same answer. So when you're pretty sure the functions are linear, you can do this. Saves you time. And this is a proper mains level question. Mains or bits, this is the kind of question they would ask you. And that is how you can solve, like, you can finish all the physics paper also in 50, 55 minutes and mains. You can't do that in advance though. Any doubts with the note? And that is a mathematical reason why it works, because it's a linear function. You can't do this with a quadratic. Look at the energy term. Energy was square, na? That's why it didn't work. Any doubts on this? Let's see one more. We have a rod, mass m, length L, Young's modulus y, area of cross section A, hanging from the ceiling. Gravity is there. So basically the rod is stretching because of its own weight. Find the ratio of elongation in the upper half and the lower half. Energy stored in the upper and the lower half. This would be a decent advanced question. Even at an advanced level, it will be like a moderate one. In this chapter, you really can't ask too much of an advanced stuff. Like, they can ask, but the varieties are little less, unlike rotation or anything else. Got an answer? You can type in the chat box here. What is the step one? You need to find tension. So let me give you a little hint. Take x from the bottom. So if I take x from here, tell me one thing. At this point, the tension is due to whom? Is it due to this part or is it due to this part? The weight hanging below, isn't it? So all this part of the weight is creating tension. So how much is that weight? M by L x into G. Okay, now you got the tension. Then you can find elongation and the energy. Now try. The tension at any point is due to the weight below it. The upper part of it has nothing to do with it. There, I gave you the tension. Try. I'll give 2 minutes. Try. Just give it a try. Get some water and come. Any answers? Right, Pushkar. First one is 3:1. Let's see. Like I said, the first thing you need to find the tension. So at a distance x from here, the tension here is due to the weight of the slice, which is m by L into x. That is the weight of that piece into G. So we get tension is mg x by L. Now, whenever they ask you ratio, right, luckily you really don't need to calculate the whole thing. We know elongation is what? Integral tension of x dx by ay. So when you take the ratio, E upper by E lower, this would be mg x dx by AYL. What are the limits for the upper one? L by 2 to L, na? The upper part of the rod, x ka values go from L by 2 to L. So the main thing is that what changes is the limits. Mg x dx by AYL. Limits will be from 0 to L by 2. mg will cancel, ay will cancel, everything goes off. You're just stuck with x dx. The only difference is the limits. Which is x square by 2, x square by 2. You can solve this. That would be L square minus L square by 4. Yeah, L square by 4. 3:1. As expected, the upper one will have a higher tension, so it will have 3 times more elongation than the lower half. Is that clear, everyone? Right, Kush, you got the second part right. Second is 7:1. It's a square function. What about energy? Energy is integral of stress is tension by area ka square by ay adx. So you can clearly see it depends only on the upper half. So energy in the upper half by energy in the lower will be integral x square dx L by 2 to L, because everything else is constant there. This would be 1 by 3 L cube minus L cube by 8. Seven is to 1. Check it out. Clear, everyone? Any doubts on this? It's a good one. Next one. Clear? Samitra? Sashwat? Clear, na? Samitra? Got this? Param? Clear this? Brijesh? Ansh? Next one. This thing we have seen in heat transfer conductivity. If you remember, a truncated cone. So we have a truncated cone like this. You are applying a force F, you are applying a force F. This is length L. We have Young's modulus Y, and this radius is B, and this radius is A. And L must be much, much greater than B minus A. Find elongation in the cone. Anyone remember what is the trick in this kind of questions? I mean, see, you need to know your tricks and shortcuts for the mains questions. What is the trick in this thing? What did I tell you in heat transfer? Whenever you get this question, what do you do to get the answer like in just like a step without any integration, nothing? Anyone remember? What is the formula normally here? Elongation is tension length by AY. So you replace area with tension will be FL by area becomes pi AB. Clear? So whenever you see this kind of question, you just replace area in the formula with pi AB and you get the answer. So remember the result. We'll see how to do this. In case you forgot, we have done this in heat transfer. Remember this? This will come 3 times. First time is heat transfer, second time is elasticity, third time is current electricity. This is how we took the elements, remember? And here, this is the final answer also. So you just replace it with pi AB. How do we do this? Try. I'll give you a minute or two. Let me help you. Let's start with this. This question is important because it comes in 3 different chapters. So this point, let's take it as x comma 0 here, and this is x is equal to L. This radius was A and this radius was B. So can you find at some distance x, you can take a thin disk here at a distance x. Can you find the radius of this thin disk? Let's start with that. Can you find R? Now that's more of a max than physics. If you have this cone, if this is radius A and this is radius B, if you go at a distance x from the left-hand side, what is the radius of that green color disk? Try. I'll give you 30-40 seconds for that. Start with that. Let's say. Now, there are a few ways to do. One thing I know, it's a linear function, so I can write r is equal to ax plus b and try to get the values. That is one way. Or, now if you take this as a x-axis and y-axis, this coordinate will be 0, comma a. This coordinates will be, this is x, comma 0. This is 0, comma 0. This is L, comma 0. This will be x, comma r, and this will be L, comma b. So what we got here is a straight line. And we have 3 points on a straight line. If 3 points are on a straight line, what is same? The slope. So the slope of this line will be, if you take any two of them, will be r minus a by x minus 0 is equal to b minus a by L minus 0. There we get r is equal to b minus a by L into x plus a. Make sense? That's a straight line. The slope must be same. Now we know how to find the radius. Then what? Same formula. Now for the elongation here, we take this thin slice. So this radius is so small. So this is your dx. This is your radius. So the elongation formula is tension length का place में dx area into y. So here tension is F only because you're pulling the rod with F and F. So tension everywhere is F. Area will be pi r square y. So we have two variables here, x and y. So I need to eliminate and get everything in one form. So what will I do? I will differentiate this. If you differentiate this, this will be dr is equal to dx into b minus a by L. This is the relation between dr and dx. So I can get it from here. So elongation will be integral f by pi r square y. I'll replace dx here with dr into L by b minus a. Limits will go from, so here r is a variable, r is the radius of this side to this side. So radius will go from a to b. Is that making sense, everyone? How did I choose the elements? So I replaced x with dr here and I substituted this thing. So from here we get dx is L by b minus a into dr. So we have replaced this guy with this thing. So now it looks big. See, that's what I'm telling you. Don't get confused between a tough question and a lengthy question. This thing is just working. Once you get the idea of radius, it is not tough. So this is simply dr by r square. This goes from a to b. What is r? What dr by r square integral? Minus 1 by r. This will be fl by pi y b minus a. This will be minus 1 by b by 1 minus a. B minus a cancels off. You end up with fl by pi a b y. Like I said, we know the answer. So you can skip all this integration and directly get the answer. Means you won't have time to derive this. Then why should you know the derivation? Because advancement, you know what they will do? They will say this y is equal to y naught x. Matlab, the Young's model is also changing with x coordinate. And then they will ask you find the elongation. Then this formula won't work. You're getting it. Most people think mains and advanced is difficult. You simply convert a mains problem into an advanced one. Have a look at this. Clear, everyone? Next thing. Searle's apparatus. Now, this is one experiment that we have. Luckily, this won't be in your lab. This experiment setup is actually huge. It's almost 2 floors. But like I keep saying in experiments, right? More than the actual experiment, the terminology is more important. You need to know the words. So the Searle's apparatus, it is actually an experiment. To find Young's modulus. So we kept on saying Young's modulus of the wire is y and all, but how do we find that? So this is how the setup looks. Where are you? There. So let me just explain you the setup here. So we have two wires here, an auxiliary wire and experimental wire. So this side, right, this thing will not move at all. This is a dead load. It is stationary. So this is the wire which you are trying to test. Let's say if you want to find the Young's modulus of a copper wire, you put a copper wire here. And here you can see the weights here. By adding the weight here, you can change the tension. So if I had to give you a simpler diagram, this is what they do. The idea is pretty straightforward. So you take a wire here, the auxiliary wire. This is your constant weight M. So this side you don't do anything. On the right side, you keep the experimental wire. And here we have this hook kind of thing, and where you can keep on adding weights. So this is mg here. So we get the tension from here. By adding more and more weight, we can create tension there, and that's how you can vary tension. Fair enough. Then what we do, we keep something called a spirit bubble. So we have something like this filled with liquid, and we have a small air bubble inside. If you ever seen this, under construction, this masons and all, they use this to, make sure the wall or something is flat. It would look something like this. Ever seen something like this? So you have a spirit inside here and you have an air bubble trapped inside. So the logic of this thing is, if you keep this horizontal, the air bubble will be exactly in the center. If you tilt this, we know the air bubble, right, will come up due to buoyancy and the liquid will be like this. So if you tilt it, the air bubble will shift. So your job is to do something to make it horizontal. You're getting it? So what will happen in the experiment, say? So in the experiment, what we do, we just keep on adding the weight. When you keep on adding the weight at some point, this is what you'll observe. The right side wire will stretch, but the left side wire will remain same. So basically the left side wire is actually for comparison. When you added the weights here, this guy becomes like this. The bubble goes off like this. So initially from this level to this level, now I am sure this is the elongation, isn't it? So here what we do, can you see the screw here? This screw here, so you rotate the screw. When you rotate the screw, it pushes the spirit level up. And here you have a scale here through which you can measure how much you have pushed it up. Is that making sense? So you pushes the spirit level up till it becomes horizontal. You keep doing this. Till it becomes horizontal. This gives us the elongation. So that is the reason of that spirit bubble. You have to keep doing it till it becomes flat again. You get in the center. Done. You got everything. We know Young's modulus will be tension, which I know is mg. L is the length of the wire, which I can measure initially. A is the area of cross section that also can be measured, and elongation is delta L. I know everything here. Put it in this formula, you'll get the Young's modulus. Is the experiment easy? Is the experiment making sense, everyone? Got the setup? So we have two wires here. When you add the weight on the right side, the spirit bubble comes down like this. So basically the right side wire got stretched. So you have a screw here. When you rotate the screw, this thing pushes it up. You do this till it becomes horizontal. Then you know how much the screw moved from this scale. Basically, the distance moved by the screw is the elongation. And mg is the weight which you have added. So you know the tension. Clear, everyone? Experiments are important. Next one. So based on this experiment, now if you keep loading this material, you will notice you have something called a stress strain curve. So how does this wire behave? So if you plot the graph between stress and strain, again, like I keep saying, whenever you think of stress, think about force, and strain, think of elongation. The graph looks something of this sort. This is O, this is E, this is U, and this is B. I'll tell you what each point means. This is O dash. This is O. This is a permanent deformation. Now, look at this thing. Initially, if you look at the function O to A, so let's name them also. So A is called proportional limit. What do you mean by this? So into the region OA, so when you keep on applying that load, when you kept on putting the weight more and more, the wire will start stretching. When the wire is stretched, initially you'll observe in the region OA, stress is proportional to strain. Basically, it acts like a spring. Basically, Hooke's law. This is what we have done till now. All the problems we did, we used this only. Hooke's law is valid. So that means whatever we have learned till now has a limit. If you pull the wire too much after a point, it doesn't behave like that. So stress is proportional to strain, and the slope is stress by strain, which is Young's modulus. So if you take this angle to be theta, so we get tan theta is equal to y. So you can actually plot a graph and find the slope for this. This of slope of line OA. Great. What happens after that? So once you cross, if you put more and more weight, now in this region, forces are linear and conservative. So whatever tension you get are linear and conservative. If you push it further, if you put more weight, then you enter a region E. E is called elastic limit. So from A to E, stress is not proportional to strain, meaning you won't get a linear function. What do you mean by that? Stress is not proportional to strain. Think of like this. Let's say initially if I apply 10 newtons, I got 1 centimeter elongation. 20 newtons, I got 2 centimeter elongation. 30 Newton, 3 centimeter elongation. So 40 Newton, I expect how much? 4, right? But I get 3.8. 50 Newton, I should get expect 5, but I get 4.6. You're getting the problem? It's not linear anymore. The function has changed. Right? So stress is proportional to strain, not proportional to strain, but forces are conservative. This is a theoretical question they asked. In which region the forces are conservative? In which region forces are linear? So forces are not linear. But conservative. Have a look at this. Yeah. Now, so what happens in the A region? So if you remove the force, there's a bit of a theory. If force is removed, the wire goes back to the natural length. So up to E, right, you're safe. It won't act like a proper spring, but nothing breaks. But if you push it further, so up to E, there's nothing there. Then we have U is the ultimate strength. So in this thing, so once you cross this point E here, things have gone bad, right? There is a permanent deformation. So once you cross E, and if you try to even remove the force, you won't come back to the natural length. In EU, even if external is removed, there is a permanent deformation. Right, and when force is removed, wire doesn't go back to the normal length. Wire goes to so the wire is permanently stretched. So we have OO dash is a permanent deformation. So this is actually, in a way, it is good for us because this is how you make wires. So this property EU is proportional to ductility. Remember what is ductility? The ability to make into thin wires. So that means higher the EU, the more better for the, more easy to make wires. Now, what happens after this? If you try to stretch more, then you're gone. So B is the breaking point. So after U, the material behaves like plastic. Now again, plastic means don't think of your plastic chair. Remember we discussed what is a plastic material? Chapati ka dough, right? If you just apply force and leave it, it will be permanently deformed. Even with a little force, it will just keep on stretching forever. Material behaves like plastic. This statement is important. That is, even if stress decreases, technically think about it. What is stress? Force. Strain is elongation. If you decrease the force, shouldn't elongation also decrease? But here, once you reach this material, even if stress decreases, the elongation continues to increase. Strain increases and finally breaks at B. So whenever you operate any material, you want to operate within the OA region. Clear with this? This is the whole story of this thing. Clear, everyone? Take a break. Come back by 7:04. We'll continue from here. There are one or two more points on this. We'll discuss this. Then we will go ahead with the next part. Any doubts so far? Anything you're not clear? There are 5 questions I can ask on in this graph. I'll tell you what are those. Take a break. Come back by 7:04 then. Come back in 10 minutes. Yeah, comes on everyone. Let's see. Great. So now what are all the questions I can ask you on this? So let's say if you have this is A, this is E, this is U, this is B. This is material 1. This is material 2. Now they'll ask a question like this. Which material has a high Young's modulus? Or which material is better to make springs? And which material is better to make wires? You tell me which material is better to make wires and which material is better to make springs. Yeah, so the first thing will be what? If you take this as theta 1, if you take this as theta 2, so basically whoever has more slope is Young's modulus. So if you can see here, material 2 tan theta 2 is greater than tan theta 1. the youngest model is y2 is greater than y1. What about which is the better to make wires? So to make wires, what should you check? The EU ka length. So between the red and the green one, you can see the green one, it is only this much, isn't it? Whereas the red one is this much. Means the green one, the moment you try to stretch little further, it will crack. Maybe it's like glass. Glass does that. It's difficult to stretch, but once you stretch up beyond a little thing, first thing will happen. Instead of stretching, the glass will start cracking. So the second question is EU, the length EU is proportional to ductility. You can clearly see here material 2 is better to make for wires. Material 1. That is one standard question they can ask you. Second thing they'll ask you is like this. In which region forces are conservative? In which region forces are conservative? O, A, E. The entire region forces are conservative. In which region forces are linear? Only O to A. You're getting it? So in the region A to E, there is no energy loss. It is just that it doesn't behave like a spring anymore. O, A. The next thing, if you have a graph like this, let's say this is O, A, B, and C. Which region is plastic? Material 2 is a better spring. It has more Young's modulus, right? It can take more tension. They can ask you a question like this. In which region is plastic in nature? You can ask yourself, what's the definition of plastic? When you decrease the force, elongation should still increase. So look at this region. From O to A, stress is increasing, elongation is increasing. Okay. From A to B, stress is decreasing, but elongation is increasing. Doesn't that look weird? You're decreasing the force, but elongation is increasing. From B to C, stress is increasing, elongation is increasing. So anytime you get a downward slope like this, AB is the answer. That is how you know something is plastic. Stress should decrease, but strain should increase, which is not a normal behavior. Clear? The other 5 questions you can get. Which is a better spring, which is a better wire, which region are conservative, which region forces are linear, which region is plastic. That is a complete thing about the longitudinal stress and longitudinal strain and Young's model. So that is one part of it. That was a major part of this chapter. And after this, we have 2 more things, the shearing strain and volume strain, if you remember shearing stress and volume stress. Next one. Any doubts so far? Any doubts on this page? Clear, Navya? Archita, Aditya, Arush, Kaushambi, clear with this? Next thing. Rigidity modulus. The symbol is eta, it just looks like viscosity. So if you take a block here, let's say the lower part is fixed. The area is A and you don't apply any force, it just looks normal. But now if you apply force on this, I'm exaggerating the figure, whereas in reality, this thing won't be so much. So if you apply a force F, the material will actually slightly deviate here. This will be your delta x, this will be t, and this will be theta. So the layers will actually slide. You can see, right? If you take your book and if you try to apply force like this, won't the layers move like this? So you have a lateral displacement. So here we define shearing stress. So it's a force parallel to the area. Is force, or you can say tension, parallel to the surface area, cross-sectional area. By cross-sectional area. Then we define something called shearing strain, just like longitudinal strain. This is relative displacement, so delta x by L. So there's a displacement between two layers by the distance between them. So in this case, it is a ground car layer and the upper layer. If you combine these two, we get the rigidity modulus, which is shearing stress by shearing strain. So all these modulus are that only, stress by strain, but which stress and which strain. This is the force parallel by area delta x by L. That's it. This is the only formula we have. This is the only thing we have. So just have a look at this. Like last time, if we compared, remember, if you take a paper and if you take a plastic sheet, which is more difficult to tear? Paper is easy to tear, whereas a plastic sheet is more difficult to tear. So rigidity modulus of a plastic sheet is more, which is easy to stretch. Paper is difficult to stretch, whereas plastic is easy to stretch. Paper is difficult to stretch. So paper has more Young's modulus, plastic has less Young's modulus. So a same material can have different Young's modulus and different this thing. Yeah, great. So this is the thing there. You can just note it down. Great. Next. So let's see a question on this. So we got a cube here. The bottom is fixed. This is eta 1 rigidity modulus. This is eta 2. So you have two different materials. What you did, you made them stuck to each other. So you kept one block and another, and you made them stick with some glue or something. This length is L. This length is 12. Area is A. This was x is equal to 0. This was x is equal to A. Now what happened when you applied the force? These things got bent like this. The upper surface got bent much more compared to the lower one. The height is still the same, but this is how it became. So this was x is equal to 0. This was x is equal to A. This was x is equal to 2A. This was x is equal to 6A. Right? This was L, this was 2L, and this happened when you applied a force F. So when you applied a force F, this is what happened, and this is a steady state. So the system has finally reached equilibrium like this. Is the diagram clear, everyone? Find eta 1 by eta 2. Because see, if eta 1 and eta 2 are equal, the shape would have been like this, isn't it? Just a slanting rectangle. But because both are different, you got a completely bent in the middle. Find eta 1 by eta 2. How will you do this? Remember, this is the only formula you have. Parallel force by area delta x by L is rigidity modulus. Think, I'll give you a minute. How do we start this? Any answers? Try. One more minute. Let's see. So the thing is, since it is an equilibrium, if that is F, this will be F here. This also will be F here. Getting it? So same force will be acting on the cross section also. Okay, we have 2, 1 is to this thing, 2 is to 1. Let's see. Now for the upper part, look at the formula. So eta is given by the tension, the force parallel to the area by delta x by L. So for eta 2, force is F, area is A. What is delta x? The displacement between this upper layer and this layer cut displacement, isn't it? Now here it is given, this thing is how much? 6A and this is 2A. So this is 6A minus 2A, that is a displacement between this point and this point by distance between them, which is 2L. Is that making sense, everyone? So you take the upper layer and the lower layer, cut relative displacement, that is a horizontal displacement, and the distance between them. Similarly, if you take eta 1, the force is same, the area is same. Now you're taking this point and this point, which is 2A minus A by L. You're done. So just divide them. So eta 1 by eta 2 will be 1 by A by L, and this guy is 1 by 2A by L. So it goes up. So 2 is to 1. Easy. So in this thing, right, rigidity modulus, either they can ask very easy questions or the questions will be tough. Any doubts on this? Let's see a little tougher one. Everyone clear what we did? Especially the second part. What is delta x by L? The displacement between this point and this point, correlative displacement. So for this upper one, this guy went to 6A, this guy went to 2A, so the displacement is 4A. Understood? Great. Next one. We have a cube here. On a smooth surface. This is the cube of side L. The rigidity modulus is eta. So there's no force. Initially it is fine. But now when you apply force, again, I'm exaggerating the figure. The cube doesn't look like a cube anymore. If you apply force, the cube actually bends. Did you ever try to pull a, let's say, if you have a rice ka bag or 25 kg bag or a 50 kg bag in the kitchen, if you catch the bag and pull, doesn't the bag become something of this sort? Isn't it? It doesn't retain its square ka shape, it becomes something else. So the shape becomes like this. The ground is still smooth. So I want you to find, so this curve, find the equation of this curve. So when force is applied, the edges curve. Remember, if this had been fixed on the ground, the story would have been different. If this was fixed, you would have got a straight line. Because tension will be same everywhere. Because the ground is smooth, the tension will vary at every point, so all will not stretch by the same amount. Think, how will you approach this? How do we proceed with this? Let's see. See. So the problem here is, you pulled with force here, we have an acceleration F by M. If you go from the bottom at a height Y from here, so here, if you take the tension T, the tension will act only on the lower part of this thing, isn't it? The tension will act only on that lower part, no? So if you draw FBD of this piece, this is the tension. So tension will be mass of this piece, which is mass by length into Y into acceleration, which is Fy by L. Is this making sense, everyone? Means as you go up, the tension increases. Obviously, na, यहाँ पे tension कितना था? F. As you come down, tension decreases, and there is no zero tension on the ground level. So the tension at every cross section is continuously decreasing. So that is the reason you're getting a curve. So now on this curved surface, at a height y, if you consider a small dy, and let's say this piece has gone small dx. So basically we are taking a slice like this. This was dy and this was dx. Now from the formula of rigidity modulus, it is tension by area, the horizontal displacement dx by dy. Agreed? Isn't that the formula? So if I arrange the terms here, I'll get eta a dx. This will be tension dy. This will be eta a dx, and tension is nothing but F by L by dy. Integrate on both sides. This will be eta ax. This will be F y square by 2L. We get y square is equal to 2 eta a by F L into x. It's a parabola. It's a horizontal parabola, meaning this type of parabola. Is that making sense, everyone? And what is the area? Area is also actually L cube, so I can do that. This will be 2 eta L cube x by F. It's a square, right? So cross-section area is also L square. Is this making sense, everyone? So I took a thin strip. I found the tension in the thin strip, and for that thin strip, that the displacement be dx horizontally for a width of dy. Substitute there, and you're done. Is this clear, everyone? This is how they'll ask in advance. But for me, advanced one, this is still an easy to moderate one. The biggest headache is people don't get an idea what to do. Once you get the idea, it is easy to solve. Clear, everyone? Next one. Next one is even better. This thing can be related to SHM also. It'll be a good advanced paragraph question. So we got a solid cylinder. This is fixed on the ground. This is radius r. This is length L. Okay. Now what you did, you started twisting it. When you try to open your bottle cap, what you do? You twist the bottle cap, isn't it? Now you're trying to twist the cylinder. So when you try to twist the cylinder, let me show you how the picture would look. Let's say if this was O, this was A. Now someone twisted the cylinder. Now in the picture, it won't be clear, but it would have become like this. This is O, A has become like this. You getting it? Theta. This thing is twisted by theta. In real life, this will be very small, maybe 0.01 degree or something. You're getting it? So when you twist this, it's called a torsional angle. You will see this thing called torsional pendulum in SHM, right? So we call this thing torsional torque. Torso meaning your hip ka part, right? It's a torso, right? You can rotate about it front and back. So torsional torque, or to put it in a simple words, we can call it twisting torque. Did you ever do this thing? When you're sitting in a swing, instead of swinging front and back, did you sit in a swing and rotate yourself and then leave it? You go front, back, front, back. That's like a pendulum actually. So this is, you can also call it as a twisting torque. Is applied on the cylinder, rotating it by theta. Twisting the upper surface by theta. Find the torque. Find the torque as function of theta. So if this was an advanced paragraph, this is the first question I'll ask you. Find the torque as function of theta. And second thing I'll ask you, find the time period for small oscillations. Then it becomes an SHM and elasticity question. Try. I'll give 3-4 minutes. Think about that. How will you do this thing? It's a pretty good one. How do we start? You need to ask yourself, does the upper surface, every point, do they move same distance? When you rotate by theta, do every point on the upper thing move the same distance? The farther you go, the more you rotate, isn't it? X theta. So if you take this distance is x, so this will rotate x theta, this will rotate more. So every layer is getting twisted at a different distance. So every point will not have same torque also. Think. It's a good one. Let's see. So at a distance x here, take a thin ring. There. So this is that hollow cylinder we are talking about. So this radius is x. So when you twisted this by theta, so this thing has gone by x theta. Correct. So when you twisted this by theta, so this entire ring on the top rotated by x theta. That thing is rotated by x theta. So for this small ring, if you apply for the thin cylinder, if you apply the rigidity modulus, that will be tension on the ring by area of the ring by relative displacement by d. Tension on the ring, we need to calculate. That was the whole thing. So tension on the ring will be eta. Area of the ring is 2 pi x dx. So we are taking a small thickness dx. So it's a circumference into thickness. And delta x will be x theta. And what is d here? Distance between the upper and the lower layer. Na? How much is this guy moving? This thing delta x is 0. So we are talking about this length. You're getting the two layers which are comparing? The upper surface and the lower surface ka distance. D is the distance between upper and lower surface. Perfect. You got tension. So what is torque on the ring then? Torque on the ring is tension into distance, which is x into tension on the ring, which would be 2 pi eta theta x cube dx by L. So what's the total torque on the upper surface? Integral 2 pi eta theta by L 0 to R x cube dx. So we get torque is equal to pi eta r power 4 by 2L into theta. That's a pretty good result. This is proportional to r power 4 by L. And this thing here is called torsional constant. So K, which is pi eta r power 4 by 2L. This is called a torsional constant. And look at the function here, r power 4 means if you take a cylinder of radius r and a cylinder of radius 2r, the 2r cylinder is 16 times more difficult to twist. And remember in the beginning I told you about a metro pillar? That's why they make the metro pillar so thick. Because every time the train goes, the metro pillar is being twisted. You need it to have a really high, this thing, torsional constant, so that it can't be twisted that easily. Do remember this thing? We will again use this in SHM. So from here, you have to find the time period for oscillation. So that is how they'll connect the chapter, elasticity to SHM. Clear, everyone? That, so rigidity modulus is what I was saying. Either the questions will be straightforward formula based or they will mess up like this. And these questions all are advanced, proper advanced on this tonto. Clear, everyone? Others do keep your cams on. That's about rigidity modulus. The third one and the last one is our bulk modulus. This thing, we really don't have too many questions on this. So bulk modulus B So this thing is based on volume stress. So if you have a body here and if you're trying to compress it from every direction, we define volume stress, which is the force perpendicular to surface area, which is actually pressure. When we define volume strain, which is change in volume by V. Change in volume from natural volume. Remember, natural volume depends on temperature. So if you combine this, we'll get bulk modulus is given by dP by minus dV by V. Let's try to understand the meaning of this. This is the formula you need to mug up. So dP is a small change in pressure and dV is a small change in volume. So what this thing is saying, dV is a change in volume. The minus sign indicates it is a compression. dV is change in volume for a small change in pressure dP. So if you increase the pressure by dP, your volume will compress by dV. So then also we define something called compressibility. C, which is 1 by bulk modulus. So end of the day, what does bulk modulus tell you actually? Higher the bulk modulus, more difficult to compress. All these modulus tell the same thing. Higher the B, more difficult to compress. You can just put down the thing in the red box. That's it. There is not much theory on this. Like I said, Young's modulus 1 has a lot of theory and a lot of stuff. The remaining two things we really don't have much. Clear, everyone? No. So bulk modulus B is dP by minus dV by V. Negative indicates compression. Let's see our question. So a gas undergoes case 1 isothermal process. PV is equal to constant. Adiabatic process. PV bar gamma is equal to constant. Find the bulk modulus of the gas in both the cases. This is how they'll combine, thermodynamics with bulk modulus. So depending on the process, the gas will have a different compression. So in both the cases. How do you do this? Think for a minute, then I'll show you one. So bulk modulus is not only defined for solids, it's defined for anything that can get compressed. So liquids, gases, solids, everything it is applicable. How do we do this? Let me show you one. Look at the first one. PV is constant. Differentiate on both sides. Then this will be PdV. Remember, it's like a UV formula there. PdV plus VdP is equal to 0. Arrange the terms here. So you will get P is equal to minus dP by dV by V, which is nothing but bulk modulus. That's it. So in isothermal process, bulk modulus is nothing but pressure. What is the meaning of this? The meaning of this is if you have a gas at 2 atmosphere pressure and if you have a gas at 10 atmosphere pressure, the gas at 10 atmosphere pressure is 5 times more difficult to compress. Isn't that the meaning of bulk modulus? Higher the bulk modulus, more difficult to compress. So what this simply tells you is if your gas is at a higher pressure, it is more difficult to compress. Can you do the same thing for adiabatic? Get it? Same story, differentiate and try to get dP by dV by V term. This is a mains ka PYQ. Anyone? PV per gamma is constant. This is also U into V. So differentiate this, you'll get dP V power gamma plus P into d V power gamma. That is 0 constant. So dP V power gamma plus P into gamma V power gamma minus 1 dV. So this will be dP plus gamma P. V power gamma minus 1 is V power gamma by V. V power gamma goes off. So you end up with bulk modulus is minus dP by dV by V is equal to gamma P. And gamma is greater than 1. What does this mean? If you compress a gas isothermically and adiabatically, adiabatic is more difficult. Getting it? Compressing a gas in an adiabatic process is more difficult than compressing it in an isothermal process. Because higher the bulk modulus, more difficult to compress. Clear with this, everyone? So keep this in mind, quite a good one. Every time they won't give like this. Sometimes they might say like this, TV power 3 is equal to constant, find bulk modulus. Then you convert this into PV power something and then differentiate. Clear? Next one. Let's say we got a lake here. Depth of the lake is H. Density is rho. Outside pressure is P naught. We have a small ball here. Radius R. Bulk modulus B. You drop this into the liquid. So when this thing is dropped into the liquid, because the pressure is more inside, the ball will get compressed. Find the change in radius of the ball. Fluid mechanics and bulk modulus, everyone. The ball is dropped into a lake of depth H. Because of the pressure of the liquid, the ball gets compressed. Find the change in radius. Delta R at the bottom of the lake. Again, remember, there's only one formula taught you. Bulk modulus is minus dp by dv by v. And assume the delta R is very, very small. In real life, it is actually very small. How do we do this? Try. This is just look at the formula. Whatever you need, everything is there only. Bulk modulus is minus dp by dv by v. So dp is change in pressure. The pressure here is how much? P naught. What is the pressure here? P naught plus rho gh. So what is dp? Rho gh, no? The difference in pressure. What is the volume of the sphere? 4 by 3 pi r cube. Then what is dv? 4 by 3 pi 3r square dr. There you got everything. So just dump it here. So minus rho gh. So dv will be 4 pi r square dr. And this thing is 4 by 3 pi r cube. So this will be bulk modulus by 3. 4 by r square will go off. You end up with the dr by r is equal to minus rho gh. So we get dr is equal to minus 3 rho gh r by bulk modulus. Done. The minus indicates it has got compressed. Does the 3 go up? I think the 3 goes up. Check. Isn't it? When you drop into the water, what changes? The pressure. How much? Rho gh. Because of that rho gh, you got a dv by v. Clear, everyone? That's your bulk modulus. We really don't have much on this. Now, in all these things that we did, there is one thing we always kept on ignoring. If you take a rod and if you try to stretch it, do you think the radius will remain constant? The radius also changes a bit. So that's given by something called Poisson's ratio. Poisson's ratio, the symbol is sigma, just a bit of a theory. So sigma is the ratio of lateral contraction strain by longitudinal elongation strain. So lateral, meaning we're talking about the radius, minus delta r by delta L by L. So if you take a cylinder, if you apply a force F, and if the cylinder stretches, again, I'm exaggerating the figure. If this was the radius and if this was the length, this guy becomes L plus dl, whereas the radius becomes r minus dr. So here the negative indicates if length increases, radius should compress. So theoretically, the value of sigma lies between 0.5 to -1. But negative values don't make sense. Think of what is the meaning of negative value. When you stretch it, length increases, radius also increases. The practical value is sigma lies between somewhere 0.2 to 0.4. Let me show. There are primarily only two questions I can ask you on this. The first one is a numerical. They'll ask you like this. So we have a rod. You're applying 100 newtons. 100 newtons. What is the tension if you apply 100 and 100? 100, right? Don't say it is 0. Don't say it is 200. Young's modulus will be given 2 into 10 power 9. Let's say sigma is given 1 by 4. Let's say radius is given 1 centimeter. Let's say length is given 2 meters. They'll give you all the data. They'll ask you find delta radius, change in radius. So we do Young's modulus is equal to tension length by A delta L. So from here we get delta L by L, which is tension by AY. Then you know sigma is minus delta R by R, delta L by L. So from here we get delta R is equal to minus R into sigma delta L by L, which is minus R. Sigma delta L by L is TA by AY. Make sense? You know everything there. Substitute and you're done. Is that clear, everyone? So numericals, they can't ask you more than this. From Young's modulus, you'll get delta L by L, substitute here and you get delta R by R. It's a straightforward question. Any doubts on this? Check out the steps what we did. Then the second thing they can ask you, this was actually asked as a P by Q. If volume is constant, what is sigma? Poisson's ratio. Sigma is 0.5. Remember the result? Let me show you how you got that. So we know volume is pi r square L. If you guys remember the power rule or put a log on both sides, you'll get log pi r square L. Just log pi to log r log L. Now differentiate this. This will be dv by v 0 to dr by r plus dl by L. If v is constant, this term is 0. And if you rearrange the terms, you get minus dr by r by dl by L is equal to half. This is nothing but sigma. Make sense? That is a proof for sigma is equal to half. And the reason why sigma is equal to 0.5 is not practical value is because when you apply a force, no matter what you do, the material will always stretch a bit. The volume will change. So that is a catch there. That's it. These are the only two problems I can ask you on this. And the last thing is the relation between Young's modulus, rigidity modulus, bulk modulus, and Poisson's ratio. These things you should definitely mug up, right? Meaning these are the kind of questions they'll ask you in CET or bits. Mains, they never asked so far. We can prove them, but we don't have the derivations. It is given in NCERT, so we will just follow them. So this is a relation between Young's modulus, rigidity modulus, and bulk modulus. Young's modulus is 2 eta, 1 minus or 1 plus sigma. Young's modulus is 3 times bulk modulus, 1 minus 2 sigma. There. These are the relations between these things. Check it out. That Ansh, I think you integrated, yeah? That R into E or something. Clear with us? So that is the last of the chapter. So like I said, all the major problems were there in Young's modulus, and rigidity modulus, but these two problems are pretty important. This twisting of cylinder and this curve of a cube. Bulk modulus, there's not much. So please make sure to go through this. There's not too many problems on this. There are like 10, 15. So surface tension, viscosity, and elasticity. This entire thing is called properties of matter. That is there in HCV and your booklet. Start doing this, right? Finish it off. And next class, when we catch up, we'll start off with SHM. So with this, we're done with properties of matter. The next class will be SHM. SHM is a, if you ask me, that's a pretty solid chapter, right? Meaning even for you